So I have a slight change to that long title. I made it even longer, if you can imagine that. Really, we were going to do two talks, one an overview and then one on the more tactical aspects of this instrument. But we decided to merge them into one talk. So this will be primarily an overview with a little bit of a discussion about the local plasma and dust environment from our ROLSES radio. Brent Gary gave a nice talk on CLPS and all the future missions. I'm going to focus on one mission in particular that ROLSES is on. It's the Intuitive Machine Nova C lander, IM-1 to Malapart A up at high latitudes. It should be an exciting fall, and given that two CLPS landings are coming soon, and actually I should say 2023, not 2003. Anyway, the payload that's on IM-1 is this ROLSES radio wave observations at the lunar surface of the electron sheath, the ROLSES radio, and the PI is Nat Gopalswamy at NASA Goddard. And actually, after this talk, I think Ben Bussey is actually going to talk more about intuitive machines and their landers. So this is a good prelude to his talk, hopefully. Let's see if I can change the slide here. There we go. Okay, so what exactly is ROLSES? ROLSES is a radio that operates between 2 kilohertz and 30 megahertz. They'll measure the electric field that's from 4 stacer antennas, 2.5 meter antennas. You can see them pictured here on the upper left. And the heart of the radio is a field programmable gate array that contains a fast Fourier transform code. And what this code will do, it will take the voltage as a function of time data stream from each of these 4 antenna and convert them to spectral data. Voltage is a function of frequency. Then the spectrum will be time averaged and stored. Now, what is noteworthy about this particular architecture is that the spectral analysis is done almost completely by the digital part of the receiver. I mean, back when I started doing plasma wave work and radio astronomy work on Voyager and Cassini, all that spectral analysis and spectral filtering was done in the analog part right after the preamp. You have to either do a super heterodyning radio, or you'd have a filter bank. Whereas the analog to digital converters have gotten so fast, you can do all of that now in the digital. These are called software-defined radios, and they're flying more commonly now. Like the radio on board Parker Solo Probe is a software-defined radio built at Berkeley. Now, just to mention, this radio is built, it's been delivered, and it's being integrated now into IM-1. It's all very, really cool. Let's see, our science objectives or science targets include measuring the local electron plasma frequency. And we'll talk about this more. It's a narrowband plasma oscillation, and from there you can get the electron density, the local. So really, using radio, it's a way you can actually measure the electron plasma density. Other targets include terrestrial auroral and human-made radio emissions. In fact, the Earth is a strong source of radio emission between 100 kilohertz and a megahertz. It gives 1 billion watts of power, and you can see why folks like Jack Burns want to get radio receivers onto the far side to get away from this really intense natural auroral radio emission and from the human-made emissions. We'll also detect planetary and solar radio emissions, and actually we're heading into solar maximum, and the solar radio burst should be really popping. We might have a chance to detect levitated or lofted dust, particularly since we're up at higher latitudes. We're going to search for that weak galactic cosmic background radiation, and the wild card in all this is, of course, the radio interference from the lander itself. And we're not sure exactly what that's going to be until the radio antennas are fully deployed. We have some idea. We'll have some idea during testing, but not a full idea until the antennas are deployed. So that's sort of our wild card right now. Now, for people who aren't radio astronomy aficionados, I show you here one of our primary products. ROLSES will make this, but this is a product from the WIND spacecraft. It's called a frequency versus time spectrogram, where frequency is plotted on the y-axis, time is along the x-axis, and intensity is color-coded here, red being the most intense. And what it nicely does, it allows us to visualize the various radio features, the radio morphology. And what you can see in this particular spectrogram from the WIND spacecraft, and again, ROLSES will see something like this, only we'll be making these measurements closer to the surface. We can see our strong type 3 solar radio bursts, radio emissions. Here's that auroral kilometric radiation. And again, this obscures measurements of that weaker galactic and extragalactic signals. And of course, that's what Jack Burns is worried about. We got to get on the far side to get away from that AKR. And so this will be ROLSES will be a test bed to see just how much the Earth will interfere with these kinds of measurements. What you can see is this line here, this narrowband line near 20 kilohertz. These are plasma oscillations where the electrons kind of move around the ions, kind of vibrate, oscillate around the ions. Oscillations at the local plasma frequency. And this is just a wonderful tone. You see it nearly at all times in the solar wind, because if you know the plasma frequency, you can get the electron density. In fact, the plasma frequency it goes as the square root of the electron density. And you can use this handy dandy little formula I show down here to get at the density. So in this example here, you have plasma frequency emission at 20 kilohertz, and you plug in the formula. That's about 5 particles per cc, and that's what you typically get in the solar wind. Now, ROLSES will make this measurement as well, and should be able to measure the local electron density closer to the surface. So, given that, one thing we can do is we can use the measurement of the electron density near the surface, compare that to the electron density measured out in the undisturbed, freely propagating solar wind from Themis Artemis to get at the surface potential at the lunar surface. Now, this wasn't in the original ROLSES proposal. IM-1 was originally to be landed at mid-latitudes, but last year it was decided to move IM-1 up to higher latitudes, and the headquarters said, is there anything you guys can do with that? How is that going to change your science? And in fact, we think this is a great opportunity, because up in high solar zenith angles, it's expected to be the surface is expected to have a strong negative surface charge to it. It's a strong negative surface potential. We know this from the SIDE experiment, the superthermal ion detection experiment, up at high solar zenith angles. And our models also suggest that the surface should be strongly negative. So if you compare the electron density as measured by ROLSES to that of Themis Artemis out in the undisturbed solar wind, you would expect the ROLSES density to be lower, and just how much lower will be a function of the surface potential. So ROLSES, along with Themis Artemis, will get that measurement of the surface potential. And actually, there is a difference between what LSEP has measured, the SIDE has measured, and what our models say. So hopefully, the ROLSES and Themis Artemis measurements will allow us to converge and understand why there are differences between the two values. The other thing is that ROLSES will be able to capture waveform data. Voltage is a function of time waveform data, and we think during those periods we should be able to detect electrostatically lofted dust. And up at high solar zenith angles, high latitudes, up in the poles, we expect that there should be lofted dust, or there could be lofted dust. For example, the horizon glow observed by Surveyor at terminator crossings is thought to result from forward light scattering from levitated lofted dust. And the lunar ejected micrometeorite experiment detected possible dust impacts, slow-moving dust impacts on its front film and grid system that peaked up at the terminator. So ROLSES should register these same kind of antenna grain contacts associated with surface lofted dust, probably along the lines of LEAM, actually. So given that we can get a measurement of the surface potential along with lofted dust, we can examine their correlation. And in particular, it's long been suspected that the levitated and lofted dust may come from extreme surface potentials. And we can actually test this now up in the polar region. So the bottom line is, even though we moved our landing site up to higher latitudes, I actually think there's a new opportunity here to do new plasma and dust science in a sort of a correlated way here that we maybe couldn't have done down at lower latitudes. In the lower latitudes, we can do lots of great studies of the photoelectron sheath, but gosh, moving to high latitudes, this looks like a lot of fun too. So anyway, it should be fun next 6 months or so. Anyway, that's the talk.